Thanks, Ben, for that introduction. So I will give you an introduction to deep learning today, and I will not pretend that in 30 minutes I can cover everything, but I'll try to start with putting deep learning a bit in a historical perspective, that we're actually already have been transitioning from end-to-end learning from your data for decades now. And then I'll introduce some neural networks 101 and some important algorithms that you will hear about during the rest of the day as well. So if you look at machine learning in medical imaging, well, in the 50s, 60s of the last century, you didn't really have any machine learning. So essentially any predictive system was completely human-based. So you had data, which could either be medical imaging or health reports or similar. And then as a human, you would extract some features from it, for example, blood tests or age or whatever you want to use. And you would come up with some thresholds or categories for these features, and that would allow you to do a prediction. And a lot of the models based on this type of system are still in use today. For example, if you look at a prostate cancer risk model, which is widely used in Europe, it essentially has three features: the clinical stage, a blood test, and a pathological assessment by a pathologist, which categorizes patients in low, medium, and high risk, which determines their treatment. And this was completely based on human observations on lots of patient data. Obviously, we figured out that with the more and more data we get from patients, the more features you have, at a certain point, it's no longer feasible as a human to figure out all these different thresholds you need for all these features. So naturally, with the rise of computers, what we did is, okay, we humans determine what data we need and what features we are going to extract from that data, but we'll let the prediction be done by a computer. And this goes from very simple, essentially extensions to these risk models. For example, this is one which was recently published on predicting lung cancer risk based on nodules on a CT. And essentially the only change here compared to that coarse model with only three features is you have a couple more. And what they did is you put this in a logistic regression, and then the computer determines how relevant each feature is. Of course, this is very basic clinical research, but everybody's probably familiar with the field of radiomics, which takes this to the extreme. So again, an example with lung nodules in CT. This is a publication from Hugo Aerts et al. In Nature Communications. And what they did is they just calculated 440 features for every nodule, and these features don't even have to have immediate semantic meaning. So they have texture features and derivatives of the image and all that kind of stuff that does not immediately ring a bell when you look at it from a diagnostic perspective. But what they showed is if you extract just all these features and you put it in a very smart computational model, then you can show that some patients with a certain lung nodule die early and some patients die later. And these are nice results, but what we're still doing here is that the humans come up with all the features, right? So 440 features, but all handcrafted by humans. So obviously, if we trust computers to figure out which features are relevant, why not trust computers to also come up with the features themselves? And that's essentially where we are now, and this has been going on for, I would say, a better part of the decade. And if you look back, for example, MICCAI, I think 2012, 2013, the buzzword at that point was dictionary learning and sparse coding and representation learning. And in the basis, it's already quite close to what we currently do today with deep learning. And so to show you an example, this was published by Coates et al. From Joshua Bengio's group at AI Stats in 2011. And what they did here on the CFAR10 data sets, which are tiny natural images, they said, okay, let's split these images into very small patches, and then we define a certain feature extractor. And in their paper, they showed that for this specific problem, the k-means feature extractor was the best. So what they did is they divided these small images into very tiny patches of a couple of pixels. And then when you cluster them, according to a certain number of clusters, you essentially get feature representations of these images. And they look a bit like this. And they also look similar to what you would expect from natural images. So you see some edges, some color-based features. And then what they did is they aggregated these features across the image and made a feature vector. And this feature vector would then be put in another classifier, which would do the final prediction. So they're feature learning, so learning the features from the data. And actually the classification problem were still two separate things. And that was quite popular back then. You also had stacked autoencoders, which did something similar. So the feature learning and the classification parts were separated. And it has one major disadvantage, namely that the feature learning part does not necessarily have to learn features which are relevant for your classification problem. And, well, it's always a bit debatable when the switch happened, but I think most people would agree that this was the breakthrough, a paper by Krasniewski et al. At NIPS 2012, where he did end-to-end training of a relatively large, for that time, convolutional neural network to classify natural images. In this case, ImageNet, which is essentially CIFAR-10, but a lot bigger, so 1,000 different classes instead of 10, and much bigger images. And in contrast to the previous slide, what they did here is you just input your image, and at the end you get one of the 1,000 classes. So the feature learning and the classification part are completely integrated. And this was mostly possible due to advances in computation systems like GPU computing, but also there were some advances in algorithmic design. I'll touch upon some of them later. So just to show you this in a more quantitative way, how big this breakthrough was at that time. So this was the error in image classification on ImageNet. You see some examples on the left. So in 2011, before this paper, we would have been stuck between 25 and 30% classification error for quite some time. And there was progress, but this progress was relatively slow. And then in 2012, thanks to his paper, we went from 28% error, we went to 15. And since then, I think last year we were at roughly 3.7%, which is relatively similar to the current human estimates we have on this data set. And whether this human estimate is accurate is a bit of a debate. But we're getting quite close to what humans can do. To reiterate again how important this paper was, it has been cited since it was published 28,000 times. To put that into perspective, that's more than 10 times a day since it was published. So I don't know of any other paper which get these kinds of numbers at the moment. So of course, we as a medical imaging community also take note of these developments in computer vision. And what I and some colleagues of mine did last year was write a review on deep learning in medical imaging. So we assessed a bit the rise of the number of papers which use either convolutional networks or other deep learning algorithms over time. So in 2012, of course, very few, but it's really growing exponentially. And last year, we had more than 430 papers on deep learning in peer-reviewed journals and peer-reviewed conferences like MICCAI. And if you look at the MICCAI program this year, I think somewhere between 20 and 30% of all papers are on some form of deep learning algorithm. So it's really, it's not just hype, it's really here to stay. That's also caused by some, I would say, results which were kind of spectacular. And I would want to highlight three. One was published by a group from Stanford early last year, 2017. And they showed that using end-to-end convolutional network training, you can classify skin lesions, photographs of skin lesions, better than 23 different dermatologists. So I think this was one of the first examples where really machine learning methods were outperforming human experts. We did something similar December last year, where we showed that pathologists can also be outperformed, 11 pathologists by deep learning systems. And this month on the cover of Nature Medicine was a paper from DeepMind, where they showed that deep convolutional neural nets can classify more than 50 different eye diseases from OCT scans. And I can assure you that this type of covers will be popping up in the near future more and more. So that's a nice background introduction on deep learning. So now a bit more on the algorithmic side. So I'd like to start with just some very basic introduction on neural networks for the people who are unfamiliar with it. And then I'd like to cover the three main types of learning that you see now in medical imaging literature. One is supervised, like the things I've discussed before. That's end-to-end training. And that's usually used for either classification or regression. And with classification, you can also mean things like segmentation through classification, for example. Then I'd like to cover a bit of unsupervised learning. For example, generative adversarial models, and variational autoencoders, which have been popping up over the last year in medical imaging, and currently they're mostly used for image generation or image enhancement. You have other use cases as well, and I think a later talk today we'll get a very good overview of all the different application areas. And I'll briefly discuss reinforcement learning, not because that's already had a major impact on medical imaging. There are some papers, but it has resulted in some of the main highlights that everybody has heard about. For example, AlphaGo beating the human world champion at Go. So back to the very, very basics. The neuron that comprises all neural networks. So a biological neuron and a mathematical neuron, or a neuron and neural network, are relatively similar in function. So the idea in a regular neuron is that they have dendrites which carry impulses from other neurons. Then if these impulses lead to a certain signal, the signal can be transported across the axon to other neurons. And a mathematical neuron is actually very similar. You have inputs from other neurons. They are weighted with learned weights, then summed together into a scalar value, and typically a nonlinearity is used to introduce nonlinear effects into the neural network, and then you get a scalar output. So for this nonlinearity, I'll only briefly touch on this. You can use very simple things. So you can either threshold the scalar value and then output 0 or 1, which is a bit similar to what our own neurons do. It's actually not very popular in neural networks. You can use a sigmoid function, which maps everything between 0 and 1. Hyperbolic tangent, which maps everything between -1 and 1. And the one that's actually most popular in most networks now is the rectifier, which is essentially a max of the input of the signal. So if it's higher than 0, you get the same number. If it's lower than 0, you get 0. And the advantage of this one, and that's also why it's so popular, is it doesn't saturate. So if you get very high values in the other ones, you don't get any real change anymore in your function. And here you do. So neurons, very simple. If you stack them together in layers, you get neural networks. Typically, neural networks are discussed in terms of the amount of layers. So here I show a 2-layer network. That's typically because the input layer is generally not considered an actual layer, because that's just your data. And the hidden layers are called hidden because they are not directly observed. So they're not at one of the ends of the neural network. And your output layer is typically either your class prediction or your segmentation map or whatever. Okay, so you have networks of neurons. Neurons have weights, and weights need to be learned to give you an optimal model. So how do you do that? Well, you either first need to define a loss function, a function which determines how you update your weights to get to an optimal result. So a very simple example, let's say I want to train a neural network which classifies between cats and dogs. Let's say I like dogs better, so they are class 1, and the cats are class 0. Then a very common loss function that is used for classification problems is the cross-entropy loss. So to give you an example, let's say the ground truth I, or y, is 1. That means that this part becomes 0, and then you have 1 times the log of the probability of your model. So if your model also predicts 1, you have log 0, so then your total loss is 0. If your model does it completely wrong and it predicts a probability of 0, then you have log minus infinity. This will result in minus infinity, and then you just get infinite loss. So and then any result in between. So the idea is that you want to minimize this loss function. So how do you do that? Well, this is a very simple example. Here you have a network with 2 weights, y and x, and a loss value of z. So you initialize your weights randomly at the start, which will put you somewhere, in this case here, at this loss curve. And what you can do is you can look at, if I perturb the weights, how does my loss function change? So you can take the gradient of the loss with respect to the weights, and that will give you information on how you should update the weights to get closer to the minimum. So if you do that iteratively a couple of times, then at a certain point you will have the weight values which are optimal for the problem you're trying to solve. Now this is kind of a toy example because you have 2 weights. So you might say, okay, if you have a lot of these layers and you have a lot of these weights, then you have to calculate the derivative of the loss with respect to every weight. Isn't that a huge amount of work? Yes, that could be a huge amount of work. Luckily, we have a very smart algorithm to help us with that. which is called backpropagation. And this animation will go a bit too fast. The general idea is that you have an input, which you propagate to the network, which gives you an output. You can put this output into the loss function, which will tell you how wrong or right the network is. And then you can take the gradient of this loss function with respect to the input of each node. So for example, if I'm here, I can take the derivative of the loss with respect to the weights of this neuron, and I can take the derivative of this output with respect to this input. And then I can do this again for this node, and again for this node, and again for this node. And in the end, you have a very long list of equations, and because you're at the input, you know all your numbers, you can fill them in, and then you can calculate the gradient for every individual weight. This sounds very complicated, and I cannot go into detail, into a lot of mathematical detail, but luckily nowadays you don't have to do this yourself anymore. We have a lot of very nice libraries from a lot of very big companies, most of them on the west coast of the US. So TensorFlow by Google, Microsoft has something, PyTorch is supported by Facebook, and I think Caffe 2 is mostly supported by NVIDIA at the moment. And these are essentially symbolic mathematical engines, which allow you to calculate any computational graph on a GPU, so very fast. Generally, you do have to build your own layers and models on top of it, but luckily also other people have done that. For example, you have Keras, which is a package where you can build models on top of, for example, TensorFlow and Microsoft Cognitive Toolkit. One package I'm omitting here is Theano, which was very popular for a very long time, but was developed in Joshua Bengio's group. But I wouldn't recommend starting to use that now because they discontinued development because they also feel that these ones are more mature. So if you see it popping up in papers, it was a very good package, but don't start, if you start with deep learning, don't start with Theano now, start with one of the other ones. Okay, so neural networks. We have different types of neural networks. So the ones I've showed you up till now were these very simple feed-forward networks, which were also called perceptrons. And where every node is connected to every next node in the next layer. You also have different architectures, for example, recurrent neural networks. I won't be talking a lot about them today, but you see them popping up in literature. The difference is that they are all connected to the next node, but they're also connected again to themselves. So if you unwrap this, then you can get another layer and another layer and another layer with the input added in again. So these are used a lot for sequence type of data, where you have to feed in the input and the next input and the next input, and then you can keep track of what you predicted for the previous one. And the one which is actually most popular in medical imaging at the moment is convolutional neural networks. The main difference between convolutional neural networks and regular neural networks is that the connections are sparse and the weights are shared spatially. So, for example, here the blue weight is shared between all these different nodes. So this causes a lot of parameter reduction in neural network layers, and it's sparse. So this blue one is connected here, 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 but not here. So this way of setting up your network helps you achieve translational invariance. So that means that essentially you learn features which are applied at every position of the image. So I'll show you in a bit how that looks in 2D. Typically, what you also see in convolutional neural networks are pooling layers, so aggregation layers, where you take the output and then use either a max operation or a mean operation to merge them together. The advantage of this is that this gives you a bit of extra translational invariance, but it also reduces dimensionality a lot. So that's good for your memory requirements. And it means that the convolutions in the layer after the max pooling essentially have twice the spatial area with the same pixel size. So that means that you can increase your context of your filters that way. So how does it... one thing about pooling layers which I want to mention is that they were very popular. They were also in the Krzyzewski's paper, but one of the deep learning gurus really doesn't like him. So the pooling operation used in convolutional networks is a big mistake, and it's the fact that it works is a disaster. So he did introduce them, but he doesn't like them anymore. And he's now a very big proponent of capsule networks, which I will not be talking about today, but you will see them around the conference. How this looks in 2D? Well, essentially like this. So it looks like a convolution, which is why they're called convolutional networks. So the shaded area here is replicated across the image. So that's essentially your feature filter, and that results in the detected features. Well, current state of the art. So back to the breakthrough in 2012. So this network had, well, arbitrarily, it depends on how you count the layers, but this had 5 convolutional layers and 3 fully connected layers. And back then, this was so big that they needed 2 GPUs to be able to run this network. So they used the GTX 570s with 1 gigabyte of memory, really state-of-the-art stuff back then. Well, state-of-the-art now looks a bit more similar to this. So this is Inception v3, is a network developed by Google. This one ImageNet in 2014, and this network has more than 100 layers. And you need much bigger GPUs to be able to infer these. Just to put it a bit in perspective, where we went from 2012 to 2014. And, well, this is expected to grow in the future as well. Okay, so now for some examples. I'll start with supervised learning. So how do you apply these networks in practice for medical image analysis? And I will show you an example of a system we developed for detection of prostate cancer in histopathology specimens. So essentially, it's very simple. What we did is we collected a lot of biopsies with annotations by pathologists, here in yellow, and then we extracted small examples of prostate cancer and normal tissue. We took a network which was very similar to the AlexNet network from 2012, and the only thing you have to do, once you have your gradient descent and your backpropagation in place, is feed in these samples, feed in the labels, and then the network automatically optimizes all the weights, like magic. Nothing you have to do. So once this network is trained, you can apply it to new cases. So in this case, I'm applying it to the old case. And the network can very nicely predict for every pixel whether there's tumor or not. And actually what I like about this example is that the green areas here are actually correctly predicted by the network as not being cancer. It's stromal tissue. But the pathologist, well, I wouldn't say he was too lazy to make detailed annotations. It's really not feasible to do this on a large data set. But it's nice that the network is actually doing a more precise job than the pathologist did. One of the nice things about convolutional network architectures is that they're very flexible. So you can shape and construct them in such a way that they are very suitable to a wide range of problems. And I think one of the nicest examples, and also one of the most widely used in this community, was the UNet, which was developed by Wonneberger while he was still at the University of Freiburg. Was presented at MICCAI in 2015. And essentially, if you look at how this compares to the network I was showing you previously, is if you go down, this part is essentially exactly the same. What he added was this upsampling path where there's a connection between the high resolution from the left side to the upsampled part on the right side. And this makes this network very suitable to do segmentations. So to show you, this was what the result they had on the segmentation of the walls in electron microscopy. And this is one example we did for kidney tissue segmentation. So on the left side you see a regular CNN where the output is nice but looks a bit coarse. And with UNet, because you also have the high resolution information and you directly predict the segmentation map, you get much nicer outlines. One more example of the flexibility of convolutional neural networks, and this was in the time when 3D convolutions were really not implemented in all these libraries yet, was again lung nodule classification, where what we did is we just took multiple views of the nodule, made multiple branches of a CNN, concatenated everything, and trained this entire thing end to end to get some sort of 3D information in there. So you can really design these things in such a way that they fit your problem. Regression, I'll just show one example. This was a Kaggle challenge in 2014, where you had to predict the left ventricular volume, or essentially the ejection fraction, where you needed to calculate the left ventricular volume from MRI time series. And what was nice here is that a lot of people thought of the obvious solution that I would also think of is first segment the left ventricle in every frame and then calculate the volume based on that. but there were actually a lot of people who didn't want to do this segmentation, so they directly predicted end-to-end. So you just put in the MR sequence and had it predict the ejection fraction. And they actually ended up in the top 10 as well. So you can just do end-to-end regression as well with deep neural networks. Then last couple of minutes of the talk, I'll have to go a bit quickly, I see. I'll talk about unsupervised learning a bit and applications. And I was planning on explaining a bit more, but I'll have to skip over this a bit. So there is a talk about adversarial networks later in the day, where this will probably be explained a lot better. The main idea is that you have two networks, one which generates images and one which tests whether they are real or fake. And the advantage of this approach is you don't need labels. You only need a data set of real images. And then once this is trained, you can use the generator to generate new numbers. Another algorithm which does a bit similar are variational autoencoders. And I'll just skip over this a bit quickly. In the end, what you can do is you can generate, for example, fake celebrities. Not sure why you would want to. Too many already, but you can generate fake celebrities with these networks. I can make myself look very old and smile. But actually for the medical imaging community, what you can also do is you can generate, for example, CT from MRI. And you can even do this with unpaired data. So for patients where you only have MRIs and patients you only have CTs, you can still train systems which predict one from the other. Now, last topic I want to touch upon is reinforcement learning, and I just want to talk about this because it has led to some high-profile successes. It's a bit different in that you don't really do a classification, but you do predict actions you should take. And the most common application area at the moment is games. So for example, here you have Pong, and the idea is you just put in the frame, and then the network should say, should I go up or down, given this game state? And actually, the easiest way to optimize this conceptually is just play a lot of games, where you just randomly pick actions. Then you backpropagate through the entire game, and then the likelihood of actions that are positive for the outcome of the game will get a higher chance of occurring. So you can still train these systems end-to-end. And I have a nice example, which I still want to show. But if you are more interested in how this exactly works, these are two nice resources to get started with reinforcement learning. And I want to show one example. So here they try to teach this game Breakout, or try to do Breakout with reinforcement learning. And you can see that at the beginning it's not great. Not good at all, I would say. But if you just keep at it and just keep backpropagating through all the games, then slowly it starts to get better. I'll just go a bit. I have to stick with it. It's 1 minute. Because the part I want to show is at the end. So now I would say it's actually much better than I am. But really after 600 training episodes, 600 games, it really starts to do things which you could consider superhuman. So now it has figured out, like the text said, that it's really the best strategy is to do this. I might think, yeah, it was a lucky shot. But actually it's kind of consistent in doing this. And this works for a surprising number of applications. And the most famous one is, of course, this, where they beat the world champion of Go. So this paper was actually about the European champion. And this was really special because at that time they said this is still 10 years away. And the main reason, if you compare it to chess, is that chess is actually a very simple game where you have limited options per turn and a limited number of turns per game. So you can mostly brute force through this. And for this, you really have to be smart. Well, for medical imaging, like I said, there are not many great applications yet. I think, for example, this would be very interesting to see for picking the right treatment for a patient. The disadvantage is you don't have a very nice simulation environment, and I wouldn't try to train a system on real patients. But what we've seen in the past, and this was presented at the middle this year by Bernard Kainz, because due to visa issues, Anasari couldn't be there, is, for example, landmark prediction. And then you just look at small parts of the image, and it has to try to find a landmark and can go right, back, forward, backward, and up and down. So, to conclude, this whole deep learning revolution, I would say, has really changed our work significantly. So if I look at my own PhD, this was roughly how I divided my time. And in the current age, it's more like this. Which sadly means that all this work, which I spent 4 years doing, can now just go to the scrap heap because I can now do better in 2 months instead of 4 years. I hope your takeaway here is please at least try deep learning for your problem, and you will see that it works very, very well. And the last slide is, of course, I go back to here. So now we're here, and I actually expect that not too long in the future, we will go here. So now we decide that we need T2-weighted MRI and T1-weighted MRI to do our diagnosis, and at a certain point, I'm quite sure we'll just feed in raw MRI data and let the computer figure out what the relevant images are. So some nice resources if you're interested to get started with deep learning. Like I mentioned, we wrote this review last year, and I think it gives a kind of a nice overview of all the papers that were out for across the field of medical imaging. So it's a good starting point to start your literature search. This is a very nice write-up how to do long nodule classification in CTs with the number 2 from the Kaggle challenge, and of course these tutorials to just get some basic ideas. And with that, I'd like to end my talk, and I'm not sure if we still have room for questions, but I'll leave that to Ben.